Hi everyone, my name is Zhao Han or Jack Wang, and I'm a second year PhD student in the School of Civil Engineering at the University of Sydney. And today I would like to introduce our recent published work, How Mandatory Are Mandatory Lane Changes, an analytical and experimental study on the cause of missing freeway exits. And this work is co-authored by myself, Professor Mohsen Ramezani, and Professor David Levinson, and this work is published on Transportation Research Part B. So first, I would like to introduce our research questions. So for this work, we want to ascertain how mandatory or not are mandatory lane changes for exiting freeways, and thereby questioning the notion of lane change. So traditionally, the concept of lane change has been classified as either discretionary or mandatory. And discretionary typically refer to when people change lane for some speed gains or safety advantages. And mandatory lane change are usually when the driver is forced to change to another lane. For example, if there's a downstream obstacle, then the driver has to change to another lane. And for this work, we want to question whether all mandatory lane changes should be considered as mandatory. And for this, we want to use both analytical model and an empirical evidence to prove this. So first, I'd like to introduce our analytical model. So let's assume that we have some driver driving along this gray dotted line, representing a freeway. And this driver has a destination represented by this cross. And what this driver usually do is he or she exits the freeway using the original exit and travel along this green path to the destination. But let's now say that he or she has missed the original exit and has to travel further along this freeway to the alternative exit, which is directly downstream of the original one. And then this person exits the freeway and then uses the pink path to the destination. So then the distance cost incurred for this person is represented by the orange part plus the pink part minus the green part. And the pink part and the green part can respectively be simplified using their Euclidean distances, multiplying their respective securities. And then based on some optimality assumption, we have quantified the proportion of people using on any location, essentially using their alternative and original exits. And then based on the optimality assumption, we quantified the proportion of these exits to be their first order, second order, and third order nearest exits. And so the only problem left to us is how to calculate the average distance or average Euclidean distance from the first order, second order, and third order exits to any location on the 2D plane. And what we have done is we have assumed that the exits follow something called the 2D homogeneous Poisson point process. And then based on this assumption, we have derived the nth nearest neighbor distributions for all the exits. Then using these nearest neighbor distributions, we could then finally derive the average distance and time cost for missing an exit. These expressions are extremely simple. They're only in terms of some network level variables, which include the df, which represent the average distance between two consecutive exits, C bar, which represents the average security on the surface tree network, lambda, which represents the sparsity of the exits, pi, which is just a constant, Vs and Vf, which are respectively the average speed on the surface street and freeway networks. And it's also in terms of the the gamma distribution, which you can regard as a constant. So here is a real life example in the New York City. So I want you to focus on this gray vehicle. So this vehicle wants to exit this freeway, but somehow missed the exit. So what this driver did is he did some very dangerous maneuver by first reversing the car and then exiting using this off ramp. But in the end, we calculated the time cost based on the 5 kilometers around this recorded location, and then it turns out to be that the time cost for this area is only roughly 2.15 minutes. So here's another example. So I want you to focus on this black car here. So again, this person forgets to change lane beforehand, so he has to do some very dangerous maneuver to exit the freeway. And in the end, we calculate the time cost to be only 1.52 minutes. So we have also conducted a simulation experiment on the top 50 metropolitan areas in the United States, and the results are actually pretty promising. So for the actual or the simulated values, what we have done is that we have calculated or estimated these values by randomly drawing OD pairs on the metropolitan networks and then calculating the shortest path for an OD pair, and then if they use some exit or they use some freeway, then we could calculate what would be the cost if this person has not exited using the final exit. And this is also compared to our predicted values using our analytical model. And you can see there's a strong linear trend between the two. The RMSE and MAE are both lower than some baseline, and this baseline is calculated based on the average of the actual or simulated values. And note that our model does not require any pre-assumption or knowledge on the actual values or simulated values. They are only calculated using the network level variables. And similarly, for the time cost, we can also see a strong linear trend here. And our analytical model has again outperformed the baseline. So now I would like to introduce our empirical evidence. So for this part of our work, we have used a dataset collected in the Minneapolis and St. Paul metropolitan area, and this was collected back in 2008 and 2009. And this is a GPS dataset which involves car trips only. And then we have just pre-processed the dataset, and then for each of the trips, we have computed their alternative path, which we assume that if the driver didn't make the final exiting maneuver, then this driver would then travel along the freeway and then to some alternative exit and then exit the freeway there. And then using this very simple heuristic, we have calculated the time cost and distance cost for missing exits for each of the trips. Okay, so here are the results. On the left, you can see that there are two distributions. The blue one is something that we've constructed without the shortest path constraint, meaning that a large portion of this distribution is actually below zero. So therefore, I want you to solely focus on the green distribution. And its statistics are shown here on the left, on the right. So first, you can see that the mean or the average time cost for missing an exit is estimated to be 1.8 minutes. And the p-value here is also very small, meaning that we could reject the null in favor of the alternative, meaning that the time cost for missing an exit is indeed positive. And here is the case for the distance costs. And again, I want you to focus only on the green distribution. And based on this, we can see that the average distance cost for missing an exit is roughly 3 kilometers. And again, based on the p-value, we can see that there is actually a distance cost incurred if you miss an exit. Okay, now I would like to conclude our presentation by discussing the findings and some future works. So first, you could see, based on the both analytical and empirical evidence, that costs for missing exits are actually not very significant. So we argued that lane changes for exiting freeways should be classified as expedient lane change instead of mandatory lane change. And second, some factors affecting the cost of missing exits are exit gap length, the security, freeway speed, and surface street speed. And finally, for our future works, we want to later design optimal controllers for expedient lane change in rational ways by incorporating the analytical model into the time, distance versus safety trade-offs.